So far, we've talked really a lot about the need to mobilize phagocytes, namely macrophages and neutrophils, and get them to the site of inflammation, wherever that tissue site might be. Neutrophils largely exist in the bone marrow and are only released into the bloodstream during times of inflammation, where they're then going to follow kind of a cytokine chemokine gradient to the site of inflammation. And this process of how these cells know where to go and actually make the exit to that site is sometimes referred to as trafficking, or the more kind of scientific term for it is extravasation, which if you go back and think about kind of your Latin root words makes perfect sense, right? Because we're going to leave the vasculature and go outside of it to the site. So that's extravasation. At the site of inflammation, there's going to be a whole lot of cytokines and chemokines that are basically going to draw the cells to the site where the inflammation is actually happening. And they're going to do this by basically making the site more permeable. So remember, your endothelial cells, which kind of line your blood vessels, are almost like barriers along a highway. You wouldn't just drive off the side of 290. There's all those brick walls on one side. But when there's actually an exit, that's a permeable area. It's a permissive area. If you're driving your car, you can just go along until you actually make it to the exit and leave. It's well marked and you know how to get there. How cells actually get to the site is one of the most fundamental things you'll need to understand about pathology and immunology. How do white blood cells get out of the blood vessels and into the tissue? In the normal state, cells are in the bloodstream and they're kind of running down a highway, much like the example I was just giving. So they're just driving along, kind of going back along the highway, speeding along, all right? As they are traveling, that's way too fast for them to note signs of inflammation on their own, unless we actually have some sort of clear sign that says, hey, you should get off here and go to that particular site of inflammation. So they have to be told to stop and enter at the exact site of insult, injury, or infection. So this process of extravasation is actually handled by a coordinated set of interactions, almost like a dance. So the first thing is, since the flow of blood is going very quickly, let's say it's going in this direction, very quickly, right? Blood vessels move exceedingly fast through or blood cells move exceedingly fast through the bloodstream. We can't just stop them right away. If we do that, that could be damaging to the cell. So they have kind of a weak interaction first, and that weak interaction is going to lead to rolling. So first it kind of stops along here and makes some sort of weak interaction. Then the cell will roll along until it reaches a tighter binding or a more stable binding. And then at that point, it's able to extravasate across the barrier, across the endothelial barrier, as is shown here. So let's talk about some of the players that are involved in this actual weak to rolling to tighter binding that leads to extravasation. So first off, leukocytes, like the one I'm showing over here, express carbohydrate-rich glycolipids on the surface, and these are known as the Lewis X antigen. In the normal state, endothelial cells lack the receptor for these carbohydrates. So the cell just keeps going across. So the cell just keeps moving because the endothelium isn't expressing a receptor for the Lewis X antigen. When we have an inflammatory response, acute inflammatory molecules such as cytokines, which I'm showing here, TNF alpha, IL-1 beta, IL-6, but even things like C-reactive protein, prostaglandins, and leukotrienes, will lead to selectins being expressed on the epithelium, which is what I'm showing here. Selectins are lectin-type proteins that bind to carbohydrates on leukocytes. Very simple. So this becomes a very weak interaction. So if I take my cell here, See if I can actually do this neat thing. I take my cell here, it's able to come over here and begin to bind with these. Okay, and as it binds, this weak interaction slows the neutrophil or the other cell down enough to slow it down. At this point, the neutrophil will start rolling along the blood vessel. The other thing that happens is that IL-8, which is produced by the endothelial cells or macrophages or mast cells at the site of inflammation, interacts with the IL-8 receptor on the neutrophil. This causes activation of another adhesion molecule, namely this one right here in pink. This is LFA1. Now, prior to it interacting with IL-8, you have a low affinity LFA1, which is a low affinity integrin. Once it interacts, once we have some sort of stimuli happening, it becomes a high affinity, okay? And once it's high affinity, it's able to actually bind more strongly. So LFA1 is typically in an inactive form, and binding of IL-8 to the IL-8 receptor on the neutrophil causes LFA1 on the neutrophil to undergo this conformational change. So I'm showing that by basically filling it in. Once it's undergone this conformational change to its active form, then it's able to bind to ICAM1 on the surface of the endothelial cells. So now it's going to be able to bind to these, okay? This is a tight binding, okay? ICAM1 is also known as the intracellular adhesion molecule, and it's expressed on endothelial cells surrounding the site of inflammation, all right? So now we've actually stopped the neutrophil from rolling. Binding of LFA1 to ICAM1 is tight. So this is a stop signal to our entering leukocyte. And this is the most horrible stop sign that's ever been drawn in the history of stop signs. But it's what makes this neutrophil that's trying to respond to stop. This stop sign tells it to stop and allows it to migrate directly between endothelial cells to get directly to the site of inflammation. Let's just make a dark, angry cloud of red and call that inflammation, okay? Now, this is a fairly complex process, but that's kind of the level of detail you need to know. You need to know that there's Lewis X antigen, which binds to selectins that come up during inflammation weakly. That causes the cell to start rolling. As IL-8 interacts with IL-8 receptor, we then get a conformational change of LFA1, which basically leads to tight binding of ICAM. At that point, the cell can go through. There are patients, unfortunately, who lack some part of this process. The process of leukocyte extravasation is highly redundant. That means there are several mechanisms that lead to leukocyte recruitment. Therefore, it's pretty highly unlikely that a patient would be deficient in all of the molecules that result in leukocyte recruitment, but there are patients who have deficits in one or more adhesion molecules, particularly if they have deficits in either LFA1 or ICAM1. Patients with deficits in these experience a disorder known as leukocyte adhesion deficiency. Now, this isn't a very common disorder. This is a fairly rare primary immunodeficiency. Unfortunately, though, it is not rare to see it on the STEP exam. This is a great way for STEP to test you actually know the concept of leukocyte extravasation. So patients with LAD develop recurrent bacterial infections beginning in the neonatal period. And this often is fatal as it impairs the infant's ability to mobilize leukocytes to the site of inflammation and mount an acceptable response. So like I said, not a common disorder in life, but it is a disorder that STEP exams favor, and we do unfortunately see some kiddos with it. So think through the steps, understand how the cells get in, and know your main players.